Thanks to the organizer for being clear. Do I speak loud enough? Fine. Yes. So because the panorama I choose to give more of an overview of several topics at the same time. So it might be a bit fast, and I'll try to be as slow as I can at the beginning, and I will cover maybe like a bit of a bunch of different. So I will explain a bit the work in the title. So first thing, cone surfaces. So I fixed G and N, so a genus and a number of markings. Right, with this condition that G minus 2 plus N is greater than. It's like the color characteristics greater than 0. And I fix also some parameters A1 to AN, so vector A of positive real numbers. Okay. And the cone surface of type GA for me is so a compact connected surface with some markings, okay, so some different points on the surface, plus a metric of constant curvature with cone singularities of angle 2pi AI at each of the vertex. Okay, so this definition does not help you much if you understand what the cone surface is. It's a bit tautological. But let's say you have 3 types of geometries. Maybe you've seen this. I allow myself to scale. I can have a metric which is either of curvature -1, 0, or +1. So it would give a spherical for +1 flat and finally. And for me, so a cone surface is something that I don't like a little piece of one of my 3 preferred domains, but still the properties of the Euclidean domain, or it's something that is obtained by doing locally 2 geodesics. Okay, so here, for instance, if you take one of these, and I take 2 geodesics which are the same length for the length of this embedded space, and I say, okay, now topologically, the boundary, the neighborhood of the dot is actually obtained by gluing my 2 geodesics. Okay, so this way, for instance, I get some angles which are always smaller than 2pi, but actually this will be more generally obtained by doing polygons in this in this domain. So here I draw flat polygons, just the polygon in the Euclidean plane. And the rules to identify is that I identify the edge B1 with B1, B2 with B2, and the only constraint to define the flat surface here is that the length of B2 is the same as, I mean, on both sides is the same. Okay? And if I do this, for instance, with this polygon, you can check that the surface that I obtain is actually just the torus with 2 markings, a black and a white one. So you can see where the edges are set. So the genus 1 surface with 2 markings, and you will check that in this case, the angles, for instance, at the white one, is the sum of the angles which are at all the images on the polygon, and this will be, for instance, A will be 2 club 4 club. Okay, so the white one will have 4 plus than 2pi angle. Okay, so this way we can have which are of any kind. Okay? So let me speak of the moduli space. Now we once again give a definition which is a bit of tautology. Okay, so for me, MGN of A is the moduli space of cone surfaces of type GA, and for now it's just a set. Okay, I will speak a bit later about like which sort of geometric structure we can put on this space. And when I say is the moduli space, I mean up to isometries and scaling. Okay, so for instance, if my curvature is supposed to be negative, I can always choose the curvature to be -1. Okay, and one thing that is good to have in mind is the Gauss-Bonnet formula that will tell you which type of geometry. Okay, the type of the geometry will only depend on the AI, and let's say, and the topological type, G and N, because the integral of the curvature is equal to sum of the AI minus 2G minus 2 plus N. So if I take an example with G and N, which is equal to 2 and 2, here what I represented is where which type of geometry I have. So if A is below this line, which I call the path line, then in this domain I will have necessarily an hyperbolic surface. In this domain, it will necessarily be a spherical space, and on the line, I will have a flat surface. Okay, for now it's pretty basic. But what's important is that if A is either in the hyperbolic domain or in the flat domain, so if A is smaller or equal than 2g minus 2 plus n, if the size of A is smaller than 2g minus 2 plus n, then there is a theorem which goes back to the 90s, which will tell you, for now, let's say it's just an identification of a set of points for now, is that there exists a canonical bijection between this moduli space of curves with given conical type and the moduli space of complex curve of genus G with n markings. So, and what I'm saying is that this isomorphism is infinity. So this means already that in the draw, LGN of A will have a C infinity structure. Okay, it would be an orbifold, but it will be an orbifold with a real analytic structure. Okay, actually, it's real analytic structure. So that's the first point. And the second point that I want to make is that in all this code, what I will do, we say, okay, now I have LGN, and I can identify it with, I choose some A, and then I get some representation of MGN. So I get a new geometric structure that will come from this identification. I think that when I will vary A, I will have different geometric structure. Okay? So the advantage is that potentially, if I vary A, then I get new ways of studying potentially MGN, which is if it's your topic of interest. Or conversely, I can use this identification to use the fact that MGN is an algebraic variety to study this, let's say, problem, these objects which are more differential in nature. Okay, so one quick point is that I will drop the spherical world. Okay, so I will only speak of the flat and hyperbolic world in this talk, especially because the theorem of 2 holds when you go beyond this flat line. Okay, so it's not true for the spherical case that you have an isomorphism. These are studied by Padov and Mondel. This will not be the thing that I would be interested in. Okay, so for me, this simplex will be called delta GN, and the boundary will be called a partial dimension. Okay, and what we will see is that something that will be especially interesting are these lines. Okay, so these lines are just defined by AI is integral. Some AI is integral, and you will see that for this specific choice of vectors, there will be exceptional geometric structure that carry more information than, let's say, any other points in this image. Okay, so this is one of the main points that I will try to convince you today, and it's something this will place on more rich and more interesting than that level. Okay, but let me be more concrete on what we do. So we'll first do the flat surface case, and then I will move to the hyperbolic world. Okay. So flat surface, I'm doing this bar GN, this partial GN. So it's a set of vectors A, positive vectors, such that the size is 2g minus 2. The goal is to define what I will define is a volume function. So I will try to motivate a bit why for the function can be interesting when we study this sort of space. But the goal is to define certain volume functions and compute it. Okay, so when I say goal, I mean this volume function was defined in the 90s, and I will say how to compute it. So let me, in general, I will assume that A has no, it is not entirely integral because it makes some problem. Okay, so first thing that you need is a system of coordinates of MGN. Okay, I told you that there is a natural infinity structure on MGN of A, so I will try to explain you how we do charts about this in this space. Okay, so I drew that my polygon that I like this genus one with 2 markings polygon. And I have this D1, D2, D3, what are they? They form a basis of the relative homology of C relative, so C relative to the marking, so in this case, x1 and x2, the 2 markings, with coefficients in C. Okay, so it's not just an absolute homology group, it's a relative homology. Okay, and what are the coordinates? What are actually the parameters that I'm using to define this flat surface? They are these numbers. Zi OI. So Zi is just complex number different from 0. And for B, U will stand for the set of complex number of module 1. Okay, so the unit circle. Okay, so the dimension of H1 of C relative to these points is of dimension 2G minus 1 plus n, and I'm associating to each vector a complex number and a non-zero complex number, and let's say a point on the C. Okay, this complex number is, for instance, like this. For instance, the complex number C1 is here. Okay, it's just this complex number. This is this complex number for C2 and C3. And why? What is this? It's how much do I have term if I go out and in and out through, for instance, V1. Okay, so for instance, in this case, what you will see is that O1 is just exponential of 2i pi over 6. Okay, so I have term by when I go out of this edge and come back on its twin, then I have term by yeah, 2i pi over 6. Okay.
So don't you want to even coming it out, how many vectors to be tangent, or I mean the starting number depends on the tangent vector at the point.
So if I take my tangents, let's say like I take a curve like this, let's start like this.
Yeah.
Then it will come like this.
I mean you get some turning. How do you measure
in any case, it would be a sign. I define it by taking the holonomy along and you take any path that crosses the edge, and you take the direction of the holonomy.
Only if the path is reversed, which your path does not have any fault starting.
You mean it's not smooth? Yeah, indeed. Like here, I'm not drawing. Yeah, indeed. By drawing does not show it. But I think it's okay. So you see, I have too many coordinates. If you take a look, so first thing, I have to take a version by C star, because actually, if I just like rotate all my polygon or scale it, I still get the same flat surface. It's an isometric surface, or the surface isometric not to scale it. Okay. But if you just take like a quick computation of dimension, okay, it's supposed to be the moduli space of curves, so at least dimension should be agreeing. So here I should have I have 2g minus 1 plus n times 3, let's say 2 plus 1 parameter. Okay, so you see that I'm off here by this 6g minus 6. This one is not too bad. Plus 3n. Okay, so I'm off by 3n. Sorry, no. By n plus 3. Okay, and from where do they come? They come from the fact that first, okay, I have killed 2 parameters by direction of C star. And then I have one equation which is just asking that my polygon close. Okay, the first equation is just saying, okay, now if I take a look at Z1 plus Z2 plus Z3 plus their rotated version upstairs, it should define a polygon that close. Okay, otherwise it could be that my 2 vectors are standing anywhere. So this gives like an equation. It's a complex equation, so it's minus 2 parameters, and then I have to fix that the angles at the xi or 2 pi ai. So this gives, let's say that it gives n minus 1 condition, because if you fix n minus 1 of the angles, the last one will be different. Okay, if you make this computation, normally you should find it. If someone wants to check that, okay.
So you want to minus 6?
6g minus 6 plus.
Maybe it's n plus 1.
Sorry, so you're saying that I want okay, does it is just the time? So at least you have the right dimension.
Adrien, we have minus 3, minus 2, plus 1.
minus
Minus 6.
minus 3 minus 4 minus 7
Oh, that's
plus 1. You can check out. Okay, and the second thing that you need when you define an analysis is to know how you change from one chart to another. And here, to define a new chart, what I do is to define this system of charts is I can actually define another polygon which is perfectly equivalent, which is obtained by cutting my polygon and then taking this piece and then doing it at a different place. Okay, and then I get a polygon which defines the same that surface. And the transition map you can compute quite quickly. Okay, you have a new vector d2 prime, and the new vector d3 is here. So you have to explain how to change from the old d3 to d3. And we can take a look at them later. The transition map will be quite simple. The only thing that I want to remark on this, let's say on this equation, on this local equation and on this transition map, is the fact that if I fix rho, okay, fix all the rho, then you see that my space is locally defined by the equation which are linear in Z. Okay, it's just a linear equation of in Z. Some of the Zi times some coefficients is equal to 0. And if I take a look at the transition map, this is still just linear transition. Okay, so this is just an action by some matrix. Okay, and this will become a more clear statement. So what I mean is to be more formal, if there exists a foliation on this base, and this foliation is locally defined by just saying the length of the foliation or the level set of the holonomy, and the holonomy, which is the map from phi 1 to u, which associates the holonomy along any path, is exactly fixing the rho in one of these charts. Okay, if I fix the rho, I fix completely the holonomy of my flat matrix. Okay, and so I have this holonomy foliation, which is okay, the leaves or level set. So I fix the holonomy, and then I get a space which is essentially varying the Zi. Okay, and theorem of Leach, the leads are actually complex orbitals. Okay, so although the space is not equipped with a natural structure of complex orbital, because I have this part which is just the angle part, the part in U is not actually equipped with a natural complex structure. The leads of the holonomy foliation are complex projective orbitals. And what's more important is when I say projective here does not mean projective in the sense of algebraic varieties. Here, what I mean is that this is the quotient by C star of some affine manifold. That is something which is locally defined by affine equation and the transition map of linear transformation. Okay, so here the word projective doesn't mean projective algebraic variety, for instance. It means that I have a projection structure on my manifold. Okay, so charts are defined by linear equation, and the change of chart respect this linear structure.
So why am I going to use the power 2D?
Yes, good question. Good question. I have 2G plus n minus 1 angle that it should total, but I have n minus 1 which are fixed by the angle condition at the xi. Yes. So actually, this means that I can say that, for instance, n minus 1 of these angles are fixed, and I choose that locally the target of my holonomy representation morphism is just let's say 2G of the remaining ones. Okay. But that's the choice. Yeah, what I mean is that by representing it by due to the 2G, I'm making a choice. Okay, otherwise you can say that it's the kernel of a torus of dimension 2G minus 1 plus n to n minus 1 to a torus of dimension n minus 1, which is obtained by just fixing the angles at the xi. Okay, so it's a quick way of writing. Okay. And you see that the dimension here, the complex dimension 2G minus 3 plus n is just 3G minus 3 plus n minus G. And G comes just from the fact that I feel 2G real parameters. Okay, now I will say that there is a line bundle on MGN of A. It's not, I cannot say that it's an holomorphic line bundle because I don't have a complex structure on MGN of A. Okay, it's just a synchrony of the whole. But it's a complex, so it's a complex line bundle. And this complex line bundle is just defined by basically the same definition of chart, the same definition of transition map, just identification by system. Okay. And this line bundle is equal to a function area that goes from L to R greater or equal than 0. And this function is simply take the area of my polygon seen as a polygon in the plane. Okay. So two things on this line bundle and this area is that L, if I restrict it to a leaf of the enucleation, so now the leaves are equal to the complex structure, and then indeed L is an holomorphic line bundle. The area is an Hermitian metric. Now, if instead I want to consider it as a total space, it's an affine space. Actually, like the projective structure on MGN of A is obtained by projected by C star, the affine structure on S star. And then area is locally in this chart, which are where the transition map or electricity that act linearly is an Hermitian quadratic. Okay. But what's important is that the determinant of this quadratic form is of the form some constant, okay, so some constant that I don't really care about, times this function. Okay, this function, and you see that it's one important point is that the determinant of this function quadratic form does not depend on which leaf I'm working. Okay, it only depends on A. Okay. And you see that this determinant, what is very important, is that it vanishes as soon as AI is integral. As one and AI is integral. Okay? So in particular, I mean, you understand, I mean, you try to grasp that that the case of when one of the AI starts to be integral, then there's something which is a bit exceptional. Okay, so this determinant vanishes when one of the AI is integral, and this would be okay, so now I've only spoke about like this MGN of A that was essentially something non-algebraic. Okay, it's a differential object. And I will try to put back some algebras. Yeah.
Can you take the determinant of the Hermitian form?
Yeah. It does. So there's a signature in the determinant
basis.
So
You have to choose a basis.
yes, but it would be independent.
Could change.
No, because you here the transition map would be in UPQ of the so the signature would be determined by.
Can you take the previous slide? Just to understand. I'm going to need the basis of that.
From this fine space.
Yeah.
Okay.
No, so on the total space, because the line bundle is, I mean, you cannot have the combination before, I mean, the line bundle is too much. So now I have to consider it as an affine space. It's an affine space of dimension 2G minus complex dimension 2G minus 2 plus A. And if I take it as like the total space of L, then now actually this function is the restriction of okay, so it's not directly the quadratic form, the quadratic form as to the vector and if you have a quadratic form, you can use exact and bar of this.
Yeah, so is the explanation going on the another space on one?
This also works on the moduli space. Here indeed. I skipped on the last slide that I was using the of space. It was the same as saying I work locally on the moduli space. But here, I mean, this one does not exist on the moduli space. This is not a okay. So now I will have something which will be algebraic actually. So I fix some value of k in, let's say, some positive integer, and I will assume that Ka is integral. Okay, K times A is integral. Okay, so at least I need A to be a rational vector. it cannot happen if A is true. And I assume, for instance, that all the OI will belong to UK. So UK for me is the group of roots of K root of unity. Okay. So if you take this example that I have above, and we think all the OI were 6 roots of unity. Okay. So in this case, I can choose K equals 6 or any multiple of 6. Okay. Then in this case, the flat metric is actually defined by a meromorphic K differential, and this K differential is simply given if I see my polygon as my sitting in C, and the Euclidean plane seen as T, then this differential is of the form dz to the K. Okay, and why is this differential well defined? It's well defined because so if I take dz and I try to take a look at the transition map, for instance, from when I go out here and I enter here, you will see that dz is transformed into rho dz. Okay, but if all of my OI are in UK, then dz to the K will be transformed into dz to the K. Okay, so then dz to the K is well defined. Okay, and you can compute the singularities of this meromorphic K form. It will have singularity only at the markings. Okay, outside the marking is just a regular K differential, and the singularity will be exactly given by the conical angle, or determined by the conical angle. And it will be singularities of order not KAI, but there is a sheet that it's KAI minus K. So log sheet. Okay. For me, I will have in MGN, I will define MGN AK to be the subspace of curves with some markings that satisfies that. So omega log the power K is OC of KA1x1 KAN_xn. In other words, it's the subset of MGN, let's say as a subset of curves with markings such that there exists a K differentials with the right order at the markings. Okay. So it's a subset, but actually it's also, I mean, this equation is an equation in the Picard rule. Okay, so it's an equation in the relative Picard rule. So it has actually a natural structure of algebraic subset of MGN. Okay, and if you're in a generic situation, actually this subset, because it's an equation in the Picard group, okay, the Picard group is of dimension G, so it's a codimension G space in MGN. Okay, and this codimension G is in some sense the same as the codimension G that we computed before. If we instead we say that MGN of K, AK, are the surfaces with polynomial valued in UK. This is exactly the same definition. And one is algebraic and one is related to the flat point of view. But in both cases, I computed the dimension and the codimension. Okay, so that's nice because potentially this gives me some tools to use to study these spaces through algebraic geometry and not just to so now we will define some measure on this moduli series. So first, to define this measure, I will define a measure on the leaves. So typically, potentially on the MGN of AK. Okay, this moduli space of K differentials, they are just union of leaves of the holonomic relation. They are very specific leaves, but they are more or less exactly the algebraic leaves, but they are just leaves of the holonomic. So on the leaves. On the leaves, what I do is I first consider the total space of M. Okay, the total space of M means I don't quotient by sigma. Okay, so it's just here I need to space with coordinates VI just with this equation. Okay, and on this space, so actually this space is too big because I can scale any surface, I can scale it as much as I want. So I restrict it a bit by saying I only consider surfaces of area smaller than 1. Okay, so in some sense, if I consider it as the total space, locally I'm taking either what you can see as both, or you can see that it's in some sense a vibration in this over the base. I consider then the Lebesgue measure on L star. What do I mean by the Lebesgue measure? Well, these leaves, we have fixed completely the rho I part. So they are just, I am just filling the ZI coordinate. Okay, I take the standard Lebesgue measure in the ZI coordinate, so dx dy. Okay, And then I push forward this measure along, forgetting this going from this line model to MGN of A. By this I mean, if I take some open substrate in MGN of A, its measure will be defined as the measure of the pre-image of this subset, only taken like with surfaces of area smaller than. Okay, so this defines the measure on the list. And now if I want to define a measure on MGN of A, what I take is for a point, I will take the measure which is the one in the direction of the polar relation, and the one in the transverse direction, I just take the pullback of the R measure. Okay? And after this definition, I mean, you need to check that it makes sense, but it makes sense because basically it's preserved when I change from one chart to another. Okay, so this measure is not very complicated. It's essentially 0y, which the standard measure dx dy from each one. Okay, and what I will call volume of my moduli space is either the volume of the total space, or if I'm interested in this moduli space of k differentials, and this is what maybe you've heard in other conferences, it's called the Mason-Rich volume, is the volume of the moduli space of k differential. Okay, but just with the measure defined on the list, okay, without taking this holonomy part, okay, the R measure of the holonomy. Okay, so there was a big business about computing these volumes for k equals 1 and 2. And this there's like much less on this. Okay, so how do we compute the volume? So first I will assume that AI has no integral coordinate. Okay, I'm putting myself in the simple case, the case where everything is graphable, but not so true. Then the first theorem is that the volume, both the Mason-Rich volume or the volume of the total space is computed. Okay, so how do I do this? So first, I start by computing the first. So the first thing to remark is that this volume. So I'm only taking this measure that was defined on the list of the holonomic computer, is actually equal to an integral over so MAK, so this moduli space of k differential, of this form taken to the power 2 minus 3 plus n. And what is this form? This form is the curvature form of my line bundle, the L, for this metric that was the area metric. Okay, so I have a line bundle, I have an emission metric, I take its curvature form. Okay. Why is this formula true? Okay, so you see that here I put a star means some coefficient that I don't want to evaluate on, and something that was the determinant of the area that we computed before, that was this product of sinus of AI. So where this formula comes from? Basically, you can open. I think it's an exercise, or I think it's an exercise in one. If you take just c to the power n, and you take the Lebesgue measure or restrict it to a ball, and in this case, so my emission metric is just the standard of Euclidean emission metric. And if I take the push forward of the Lebesgue measure from my ball to the projective space, it will be a power of the Fubini study form. Okay. So what I'm just saying here is that I'm using this thing. Okay, so here I'm patching together like pieces which look like affine spaces. So it's still true on these spaces which are affine spaces instead of just taking CA. And that's a bit of the trick is that I'm not taking just the standard Euclidean measure on CA. I'm taking something that has some signature and some determinant. Okay, and so the determinant will just come in here. Okay, so it's the same. Just you have to apply it to a case where your quadratic form has some data. Okay. So I will write this as volume is equal to 1 over product of the sinus AI pi times a function that we call VGN of AK, and the VGN is just this integral. Okay, and this is an integral. Second step. Now when we speak essentially of this, because if I can compute this, then okay, I have some purely determined coefficient, then I can compute this. So if I speak of this one now, there's a result by Constantini, Goethe, etc. that says that this number, you see, I define it as the integral of the curvature form taken to the top power. But actually, you can find a compactification of NAK, which is an algebraic compactification, which is smooth, and on which you can control the growth of this emission of the areas emission metric along the boundary. What's interesting is that it means that now this number is just the top intersection of the Chern class of some line bundle on an algebraic space. Okay, on a proper algebraic space, proper smooth algebraic space. Okay, so I can use now tools of algebraic solution. Now I have to shorten the names to make the slide nicer, but I'm not of the edge to shorten. So it's by Holmes, von Schmitz, and Schwarz. And they gave a way to express the cohomology class of, so the closure of this moduli space of K differential inside MGN bar. And here MGN bar is the usual algebraic compactification by stable curves of MGN. Okay, and I gave a way to compute this thing in MGN. And if you mix all of these ingredients and you work with it, then you manage to explain that this thing is actually computable. You reduce it to some intersection theory on this. And because this is computable, then you manage to find out that this number is computable, so the volume is computable. Okay, so
the star depends on some G and N, or what?
Yeah, it depends on G and N, and it's 2 pi, 2 pi, to some power. It's something really like a combinatorial.
Sorry.
Yeah.
This is a lot similar to the volume of the moduli space hyperbolic surfaces with boundaries.
So we come to this. So I will go to this later. This is what, in some sense, waging, but this is my main point.
Okay.
So I'm done with the first part of the theorem, and now I want to go to the second part of the theorem. So I know how to compute this. So how to compute this? Well, I will simply use the fact that the part of the measure that I'm missing is the part which is not along the leaves, is along this others, the target of the holonomic foliation, and the holonomic summation that defines the holonomic foliation. Okay, and what happens is that I can approximate the R measure of the sample, just considering the measure which is derived on K fruit of unity. Okay, so if I take only the K fruit of on a circle, and I take K that infinity, then this would give me some measure that approximate the R measure. Okay, so this way I can approximate this R measure that I'm pulling back to define the measure that was defining this space by approximating it by this Dirac measure on the UK. But computing the Dirac measure on the UK wedged with the measure on along the leaves of the holonomic foliation simply means computing this volume, is because we said actually the Fourier space of K differential is exactly the pre-image of UK to the power of 2G. So by definition, it's the pre-image of this. So if I wedge my measure on in the direction of the leaves with the Dirac measure on UK, what I get is exactly Gaussian of AK. So this thing is just the limit, the volume of G and A is just the limit of the volume of K differential divided by K to the 2G, and K to the 2G is just here to say actually it's not the Dirac measure, but 1 over K to the 2G times the Dirac measure that converges to the R measure on this. Okay. And if you do this, and you can try to you have to control. Okay, so you get some formulas for Volgian of AK, and then you have to control its growth as K goes to infinity. Okay, and to do it, you need a result by Pixton and Spelier, which is some let's say folklore fact that was wrong in this domain. That is that actually the class here grows like K to the 2G as k goes to infinity. Okay, it's another statement, but essentially what I'm using is the fact that this class will grow as something times k to the 2g. And then once you know it, you have to work a bit more, but then you can show that this thing will grow as k to the 2g as k goes to infinity. So it has a limit, Vgn of a, and so the limit is computed. Okay. Any more questions?
Well, maybe you have.
Yeah.
The computer means that you write it as an integral over mgn bar.
So you mean the limit?
No, before.
This
Already.
So,
All
sorry.
the gn AP.
So there's a bit of a difficulty here. This line bundle does not extend to mgn bar. Okay, so this is the big difficulty. Is that you see you have this space MAK, which is just a subset of mgn bar. Okay, so I can take the naive thing, which is just take the closure in mgn bar. But this is not it. Okay, this is bigger. This is the variation of this thing. But more importantly, this line bundle does not descend to line bundle. So you have to do your computations. Okay, so these computations, all these computations cannot be reduced to simple computation of mgn bar. And all the trick is to manage to reduce the computations of things in this space to computations in mgn. Okay, because unfortunately I cannot extend this line bundle that is well defined inside on mgn on m of a k on the open bar, but I cannot extend it to this.
End of the day, you get a formula expressed in total logical classes on MGN and any computer program that is going to manipulate that.
What I get at the end of the day is an expression in terms of numbers. Like I have some function. But yeah, indeed, okay, we can say that the Vgn of AK can be expressed as a sum of integrals over n. Yeah, indeed. But what I should say very quickly is that now, with result of with Constantine and Schmidt, the recursion, I get recursive formula that computes this Vgn of A. Actually, we get recursion formula for this and for this. The recursion formula for this are absolutely awful, but the recursion formula for this are kind of nice, and you don't need to do any intersection number. Like now, I mean, at least what is hidden in the background, but that's like a recursion, which is very explicit for this function. Okay, I don't have time to write it on the board, but it's a very explicit thing, where you don't see anymore any intersection, because we have computed them for. Okay, just some graphics for people who are lost. Okay, so here I'm taking example in genus 1 and genus 2. Okay, genus 1 with 2 markings, genus 2 with 2 markings. Okay, I have this constraint that A1 plus A2 is something, so I have only one free parameter. Okay, I have only one parameter that is allowed to move. And so the thing that I'm interested in is this Vgn, the volume. The volume is downstairs. But the thing that I start by computing is this Vgn. And Vgn is actually not like any function, it's a piecewise polynomial. Okay, you don't necessarily see it when you take a description, but it's a piecewise polynomial. Here, what I've plotted is the value of this Vgn as at rational numbers. Okay, I've only plotted the rational numbers, you don't see it with your eye because you cannot distinguish rational real numbers. But okay, up to a certain coefficient, this is product of sinus of AI by times Vgn. So what is logical? It's the fact that here, I have some zeros of this piecewise polynomial. Okay, but what is interesting is that actually, in this case, I have n is equal to 2. So this coefficient is something of the form basically like sinus of a1 pi to square. Okay, so when I plot this function, this one is this function divided by sinus sine of ai pi to the square. Okay, so it vanishes. Here you see that you have a vanishing of order 2, and this is logical. And actually, the limit on both sides is the same. But this is difficult to do. Okay, it's difficult. It's not like a one-line. Okay, so here you have if you compute the limit on one side of VGN divided by this determinant or on this side, we have the same value here. Okay, but this is what appears quite clearly on the graph, but to prove it, you have to do something. Okay, so PRN, this volume function that I compute as rational numbers extend to a continuous function. Outside of the integrals, it's obvious. It's just a piecewise polynomial divided by an empty function. At the integral, you have to say something. You have to say something. In particular, it implies that the volume is always finite, which was not something known. Okay, like Beach defined this volume, but he didn't know how to compute any of them. So in particular, even if you give me a real number, I know that it's finite because it has to be smaller. At least it has to be smaller than this function. The volume function is bounded by, let's say, the continuous extension of this. Okay, natural conjecture is that actually the volume, this volume is actually continuous. So actually what you see is actually the volume, but I cannot prove it for now. Okay, I cannot prove it for now because you have some work to do if you wanted to prove that this volume function defined by Beach is it's not an obvious thing. But for now, for what I will say next, I will assume that it's okay. I will hide on like in the background that actually when I write volume, I mean continuous extension of what I computed in the version. Just some history on this thing because I forgot to write it. The only case that was known before was genus 0 and some restriction on the markings on the weights, and it was a paper by Macmillan in the around 2000. Okay. Just a quick.
Can you say about the differentiability?
Sorry.
What can you say about differentiability?
Differentiability. Well, at some point you have to break because it's not a polynomial.
Sure.
And I think you have to break like directly after continuity. Maybe I think I checked and I think like basically just after continuity it's okay. Okay. So now I'm seeing that I split my n into two parts. One part which is so to the S and L, and the all will correspond to all markings with integral values, and the others are non-integer. Okay, so I repeat, my VGN of AK, which was this integral of some algebraic line bundle, top intersection of the jump class of an algebraic line bundle. Is product of the sinus A sine AI times the volume. So it's 0 when at least R is greater than is different from 0. Okay, so I have to find some other intersection number if I wanted to represent my volumes as integral of intersection number. Conjecture, and here my star is once again it can be made precise, but very precise. Is that actually what I should put instead of this? So I have still this C1 of this line bundle, which is in the background, but I should replace at least part of this C1 of L, otherwise I get only 2. And the conjecture is that for each of the marking which are integral, you should just put a psi I. So I don't give for you like the definition of the psi I if you cannot say it's a bit of a pity, but I will invite you. But that's pretty. Okay, just a quick remark on this problem. So it's more or less completely open. This conjecture. It holds for k equals 1. Okay, so it was the result with Cergy-Pontoise and Sauvaget. And so for k equals 1, I have to adjust a bit like the definition, but let's say another holds for k equals 1. And I will just explain one corollary of this thing because it will motivate why I'm taking volumes. I told you I define a volume and I compute it, you can say that. Why? Why? So one thing which is interesting is that if you take some of one differential, so it's essentially a flat surface in which there is no holonomy. Okay, there is no phenomenon of holonomy, so it's one differential. Okay, and on this flat surface, I define a function which is I pick two of my singularities, x1 and x2, two different singularities, and I will count geodesics of length smaller than L, okay, I fix some parameter of L, and I count geodesics of length smaller than L. the modulo theta here means up to, actually I'm not counting the geodesics, I'm counting the periods of the geodesics. So this is what the modulo theta means. But never mind, I'm counting geodesics that goes from x1 to L. And the corollary of this theorem, the fact that actually this formula holds, let's say, for k equals 1, is that this number, this function, this number of geodesics of length at most L grows like pi L squared times a very simple expression, just the product of the angle at the singularities. Okay, so it has a corollary on, like, it's not true for a given curve or for a given flat surface, but it's true for almost all deformation of my original surface. Okay, so it has some consequence for the study of dynamical properties of flat surface. Okay, so this is the motivation. Okay. Just now for recent results, actually this formula holds true at infinity. That is, when I talked about like volumes of moduli space of flat surface, it's true that this formula holds, and by it's true, I'm cheating a bit because here what I put as volume is not volume, but it's the continuous extension of the volume QT at rational number. Okay, so this formula, what I'm writing here is that if I take the graph that I took, I take the definition of the volume at an integer to be the limit, to be the one that I see on the graph, then actually it's expressed by such a formula. Okay, so it's true at k equals infinity, and unfortunately the case of k equals 2, 3, 4, and so on is much more complicated. And the proof is based on the fact that we can compute these things more or less explicitly thanks to results with constant image. Okay, now I can go to the hyperbolic world, and I have not so much time to go to the hyperbolic world, but that's fine because I've more or less set up everything you need to do. Okay, so now I will only be interested in this simplex, and I have the same rule as before, which is define the hyperbolic function. And compute it, okay? And this volume, I just change all my notation. I put an if, say it's hyperbolic instead of okay. Okay. So the first thing that I want to speak about is the small angle case. Okay, so at the beginning I will assume that my angles are small, and okay, I'm just drawing some surface here, just two surface. So I didn't draw it as it's not actually hyperbolic. For the drawing that I did, okay, and small at the beginning will mean AI smaller than 1/2, so angle smaller than pi. Okay, and if I do this, what is nice is that there exists pair of pairs decomposition. So if you have ever seen moduli space of hyperbolic surface, let's say for example closed hyperbolic surface, or if you have even better seen moduli space of hyperbolic surface with geodesic boundary, for example, studied by Gazzarani, you will be familiar with this. If not, then what you have to understand is that these things are geodesics. Okay, and you see, I think my surface in using geodesics, and in each component, I assume that I have 3 boundary components. The boundary component can either be the side of one of the geodesics or the conical singularity. Okay, so for instance, here I have 2 geodesics plus the conical singularity. Okay, so this is only a pair of planes decomposition. And so related to this pair of planes decomposition, there is a system of coordinates. Okay, so now I have a very different system of coordinates compared to the flat surface world. And these are called the French Nielsen coordinates.
Okay.
And yeah.
Any hyperbolic surface has a pair of planes decomposition. You mean probably there exists specific pair of planes decomposition with some extra property.
Yeah, so indeed. What I'm saying is I draw a pair of planes decomposition, a topological one. Okay, I'm drawing this only a topological picture, and now you fix an hyperbolic surface with point singularities, then there will be a unique representative of this topological loop, this topological simple curve, as a geodesic. Okay, and so this is the definition of the function with the coordinate. Is take the unique representant in the homotopy class of this loop, that is geodesic. Then the first coordinate that I need to define is L, is the length of this geodesic for all of these curves in the pair plane decomposition. Okay, so the first part of the coordinate is L, is just the length of this curve if I take the unit representant, which is geodesic. Okay. Second parameter is tau. Tau is what? I will, unfortunately, I didn't draw it, but I will just explain quickly. Suppose that I have this fixed hyperbolic surface. It has fixed length of geodesics at all this curve. Okay, so at all these curves, it has fixed length of geodesics. There's another way to define the surface is by cutting along this curve, this geodesic curve, and turning a bit and doing that. If I take a look at how much I have turned, this is this parameter curve. Okay, this gives me two parameters, which is either I increase the length of the geodesic or I whip and I go back by some parameter. So these are the potential distance coordinates. It depends on having chosen one specific choice on pair plane decomposition. But if you do go from one pair plane decomposition to another, you can try to write what are the maps with the charts. They are very difficult actually to write. But what's important is that there exists a symplectic form, which is usually called the Baker symplectic form. And this symplectic form actually is coordinated Li to I, or Dumbo coordinates for the symplectic form. So it's just this symplectic form. It's a very simple expression. But this symplectic form, actually, you can find a compactification of the volumetric space of hyperbolic surface in this case. Okay, if I remove this constraint, I can find a compactification of the volumetric space of cone surfaces, hyperbolic cone surfaces of type A. That is actually just the same as MGN bar. So in this case, MGN bar is the right compactification. So not at all the case in the practice. So here MGN bar is still fine to be the topological support of the compactification of MGN of A. Okay, and the symplectic form will extend to a curve. And actually, what happens is that if I integrate the top power of this symplectic form, I get a polynomial. Once again, to some coefficient, and this polynomial is if you know this classes, there's a psi class and there is a curve. And you see that it's a polynomial because I have dependence here in AI to the square. If I take exponential here, does not mean exponential, it means this thing taken to the power of 3g minus 3 plus n over 3g over factorial 3g minus 3 plus n. Okay? So it's a polynomial. It's a polynomial. Actually, in the AI. Now, if I get to AI, I want to take angles which are not general, but slightly bigger. And this was treated now extensively by this filter, and I made a mistake. Okay, so now I authorize angles up to 2 pi. Okay, and actually things now get messy. Actually, there's a long line of work that did part of this case, but now this is the right choice. So there is no necessarily a perfect position. This is one of the main points. Is that look, here actually assume that X1 has a very big conical singularity, actually bigger than 1. Okay, like 2, for instance. Then you can check that the GAUS Bonnet formula just for this surface, this pair of pens here, will tell you that they cannot be a metric with negative curvature. Okay, you just need to apply the GAUS Bonnet formula. So this is not a good position for if my conical singularities get too big. And this will happen if I allow now the AI to leave this one part. Okay, but still I actually still have a symplectic form on MGN of A, which is still a very strong form because it can also be defined abstractly. Okay, so I don't have this downward coordinate, but it's still a curve. And it does not extend now to MGN bar, it extends to, for those who have seen what it is, the asset compactification of MGN. So it's a compactification of MGN that depends on the stability parameter. And so it's a compactification that depends on the temper in which you pick your stability parameter. Okay, so now you have a phenomenon of wall crossing that is you will change the compactification. And so your integral will be a piecewise polynomial. Okay, so because I'm like way out of time, I will skip this part and go to basically the touch. So I will still use a K differential type of approach. I will define a function PGM E, so hyperbolic with A of K, but now A is not a vector such that the sum is of the AI is 2G minus 2%, which is smaller than 2 minus 2%. Okay, I have another function which is essentially the same. But the difference is that now this function, we can show that it grows at K to the 6G minus 6%. Okay. So it's equal to some function plus a big small O. And now this function, this VGN of A, is a piecewise polynomial that can be expressed in terms of the Miata-Hani polynomial that we're computing the Peterson volume in the very small angles. Second property is actually equal in many chambers, so I can check numerically that is true for all the cases that were computed by normally and Lane. But I cannot prove that it's true in generality, but you can prove formally that it's true for a bunch of but it's actually true. VGN of A is equal to 0, and I will come back to this in 2 seconds. This is like the most important property. If A has an integral coordinate, so same thing as before. And VGN, if I divide by this sign product, is continuous and greater or equal than 0. This is basically the same as I was proving before. But now you see this default polynomial is with 6G minus 6%. It's a different range of this wide polynomiality as well. And the option that I wanted to give in the hyperbolic case is that actually this vanishing is extremely interesting in the sense that if you take a look just at the vanishing, if I plug the number 2, okay, it's an integer 2, then this thing will vanish. And because actually I can express VGN plus 1 in terms of the Mirza-Kani polynomial, this gives me, as like a bunch of combination of Mirza-Kani polynomial, this will tell me that I have some relation between this Mirza-Kani polynomial because this function vanishes when n plus 1 is equal to 2. This is the expression, which is very complicated. But if you work a bit, you find out that it's Mirza-Kani's original recursion for formula for PGM, and this is actually exactly the statement. It implies the statement of the Witten-Koncevich theorem, that is, there are sort of length for the integrals of this type. So this tells you that using the existence, using this vanishing, you can prove that you can compute this integral of psi classes inductively. And this vanishing, this is the main point of my previous slide, is essentially due to the existence of isolated infoliation on this Fourier space of hyperbolic surfaces with consingularities of integral. Okay. So I stop here with